right, strap in everyone, because today we are going deep, deep down into the subatomic world.
Oh, yeah, diving headfirst into the quantum realm.
You guys sent in not one, not two, but three whole research papers about, well, a whole new model for how particles work.
And I gotta say, it's pretty wild stuff.
It really is. It's like rewriting the physics textbooks.
It is. What I find fascinating is how they take this super complex stuff, particle physics, and try to explain it with stuff we all know.
Exactly. Like, hey, maybe the universe isn't that complicated after all.
Yeah, using things like sound waves or those springy things.
Yeah, the spring mass systems, like from high school physics.
Totally. And all three papers start with this idea of a space-time lattice, like the fabric of the universe, you know?
So like the very foundation of everything, the underlying structure.
Exactly. And they picture it like a giant 3D grid.
Oh, like a cosmic Lego set.
Yeah, exactly. And each tiny block in this grid, it's called a unit cell.
Okay, so like the smallest possible piece of this universe, Lego.
Right, and each cell has this thing called a granule in it.
Granule. Okay, and what are these granules made of? Some even smaller particles.
Well, that's where it gets really interesting. They say these granules have properties based on Planck units.
Ah, Planck units. For those who may not know, those are like the smallest possible measurements in physics.
Yeah, the absolute minimum, like Planck length, Planck time.
The tiniest tick of the clock, the shortest distance, Planck mass.
You got it. And the paper suggests that these granules, with their Planck scale properties, they're like the fundamental building blocks.
So these granules are like the tiniest Lego pieces that make up all the bigger Legos, all the matter and energy.
That's what they're proposing, that everything we see, everything we are, comes from these Planck scale granules.
Okay, so we've got our universe built from these tiny granules, but how do we get from those to actual particles?
That's the cool part. See, instead of thinking of particles as little solid things...
Like teeny tiny billiard balls whizzing around.
Yeah, they say particles are actually points in this space-time lattice called wave centers.
Wave centers.
Yeah, points where energy kind of converges and reflects, creating patterns, handing waves, actually.
So an electron isn't a tiny ball, but like a point in this lattice where energy is doing something funky.
Exactly. Think of it like dropping a pebble in a pond. You see those ripples.
Yeah, expanding outwards.
Now imagine those ripples, but they're interacting with ripples from other pebbles, and at certain points, boom, stable patterns emerge.
And those stable points, those are the particles.
You got it.
Whoa, my mind is starting to bend here, but how do those wave centers and standing waves actually explain how a particle forms?
Okay, remember vibrating guitar strings. There are certain points that stay still even though the string is vibrating, right?
Oh yeah, those nodes, defining the shape of the wave.
Exactly. So the papers propose that particles are pockets of energy trapped within those standing waves.
So the standing wave defines the boundaries, gives it structure and mass.
That's the idea. The energy is contained, giving it mass because of the standing wave, not because it's a solid little ball.
Wow, the standing wave gives the particle its identity. This is some deep stuff.
And here's another mind blower. They think the most basic particle, the neutrino, might be just one single wave center.
You're telling me that tiny, almost undetectable thing might be the key to all matter? That's a big claim.
It is, and it gets wilder. They also try to explain how particles are created and how they decay, all through these wave centers.
Okay, I am ready. How do they explain new particles popping into existence?
Imagine those neutrino-like points, those wave centers, coming together.
Okay, bunching up.
But they come together in specific ways, creating constructive wave interference.
Constructive interference, so the energy increases, builds up.
Exactly. It's like merging drops of water. Each wave center adds to the energy, creating a heavier particle with a stable standing wave.
A bigger, more complex particle? Fascinating.
Right. And for particle decay, imagine an unstable structure collapsing, like dominoes.
Oh, one wrong move and boom, the whole thing goes down.
Exactly. In unstable particles, the wave centers are arranged in a way that can't sustain the standing wave, so they break down.
Releasing energy as they decay into smaller particles.
Exactly. It's all about those wave centers and how they interact.
Okay, we got tiny granules making up space-time wave centers, creating particles, standing waves, giving them structure, and everything's constantly interacting and changing. My head is spinning, but in a good way. But where does geometry come into all of this? You mentioned something about platonic solids earlier. What are those and how do they fit into this model?
Okay, so platonic solids are those perfectly symmetrical 3D shapes, like the tetrahedron, the cube, the ones from geometry class.
Oh yeah, I remember those. But what do those shapes have to do with particles?
Well, for those stable standing waves to form, the wave centers need to be arranged at specific distances. And guess what? Some of these stable configurations, they match the shapes of platonic solids.
Wait, so you're saying particles like electrons could be shaped like tiny pyramids? That's pretty wild.
It's one of the possibilities they're suggesting. They think the electron might be this complex standing wave with wave centers arranged like a tetrahedron.
So instead of picturing electrons as tiny balls, we're now thinking of them as tiny pyramids of vibrating energy. It's blowing my mind.
It's definitely a new way of looking at things, and it gets even more interesting when we start talking about those composite particles like protons and neutrons.
Okay, I'm ready for more mind-bending concepts. What's the story with composite particles?
Well, they suggest that protons and neutrons, instead of being made directly from wave centers, are made of stable particles arranged in specific patterns.
Wait, so it's like atoms are made of smaller particles, and some particles are made up of even smaller, stable particles. It's particles all the way down.
You got it. And this actually might explain a big mystery in physics quarks.
Quarks, those things that are never found alone, always in groups.
Exactly. This model proposes that quarks might not be fundamental particles at all.
What? You're saying quarks, those things we've always considered fundamental building blocks, might not be fundamental.
That's what they're suggesting. They think quarks might emerge from the breakdown of these composite structures. Like they're not really there as independent thing, but they pop up when these composite particles break apart.
Okay, my head is officially spinning. We've gone from tiny granules to wave centers, standing waves, platonic solids, composite particles, and now we're rethinking quarks. This deep dive is living up to its name.
And we're just getting started. These papers go even further, trying to explain how all the fundamental forces, like gravity and electromagnetism, come from the interactions of these waves in the space-time lattice.
Hold on, not only are they proposing a new model for particles, but they're also trying to unify all the fundamental forces into one framework. This is getting seriously ambitious.
It is ambitious, but that's what makes these papers so interesting. You know, they're not afraid to just like throw out the old rule book and come up with something totally new.
Yeah, they're really shaking things up. So how do they try to explain all these forces, gravity, electromagnetism, all that, with this space-time lattice and these wave centers? It seems like a pretty tall order.
It all comes down to how these waves interact with each other, right? Inside this lattice, imagine it like a giant cosmic game of billiards.
Billiards.
Yeah, but instead of those solid balls, you've got these wave centers and their energy fields, and the way they bump into each other and interfere with each other, that's what creates the forces we see and feel.
Okay, so it's all about the dance of the waves, but how do they explain specific forces like, say, gravity? That always seems so different from the others.
Well, let's start with the strong force, the one that keeps those quarks stuck together inside protons and neutrons.
The glue of the atomic nucleus.
Exactly. In this model, the strong force is just, well, the direct reflection of waves between those wave centers. It's like the simplest interaction they propose.
So wave centers bouncing waves off each other, that's the strong force. Got it. What about electromagnetism? How does that fit in?
Now things get a little more nuanced. You see, remember we talked about particles having spin, that kind of internal rotation?
Yeah, like a tiny planet spinning on its axis.
Right. Well, they say the electric force comes from the law of what they call longitudinal wave energy, and that loss is because of spin.
Hold on, back up a bit. What's longitudinal wave energy?
Okay, think of sound waves. Sound waves, they travel in the same direction as the energy they carry, right? Straight ahead, that's longitudinal. Now, picture a spinning particle inside the lattice.
Okay, I'm picturing it.
That spin, it takes some of that straight ahead energy, that longitudinal energy, and converts it into a different kind of energy. And that conversion, that loss, that's what we experience as the electric force.
So spin cycles off some of that longitudinal wave energy and bam, we get the electric force. Pretty neat. But what about magnetism? Is that related to spin too?
Oh, absolutely. They say magnetism is the gain of transverse wave energy, also because of spin.
Okay, more new terms. What's transverse wave energy?
Okay, think about those waves on a string. You flip the string, the waves go up and down, but the energy's moving along the string, right? Perpendicular, that's transverse. So the spinning particle, it's not just losing some longitudinal energy, but it's gaining transverse energy too. That gain, that's the magnetic force.
So spin messes with the balance between these two types of wave energy, and that creates both electricity and magnetism. Pretty slick. But what about gravity? That one always seems like the oddball out.
Gravity, according to these papers, is the most subtle force of all. They call it a shading effect, caused by that same energy loss due to spin.
Shading effect. Now that's intriguing.
Imagine two particles both spinning, right? And because they're spinning, they're each losing a little bit of their outward wave energy. It's like each particle casts a little shadow in the energy field around it.
Okay, so they're creating these tiny energy dips around themselves.
Exactly. And that imbalance, that slight pull towards each other's shadow, that's what we feel as gravity.
So gravity isn't a separate force, it's just a side effect of how spin affects the energy flow in a lattice. That's mind-blowing.
It is, right. And the really amazing part is these papers don't just explain these forces, they actually give you equations to calculate particle energies based on these wave interactions.
Wait, they have actual equations, like math equations.
Yeah, and you know what? They use equations similar to the ones we use for like springs and sound waves, stuff you might even remember from high school physics.
You mean they can calculate things like the energy of an electron using equations that are based on classical physics concepts? That seems almost too simple to be true.
It does, doesn't it? But the crazy thing is, these simple equations seem to be accurate. They predict the energies of different particles really well.
So they're not just hand-waving and saying it's all waves. They're actually crunching numbers and showing this model can produce real-world results.
Exactly, and that's what makes this so compelling. It's not just a cool idea, it's actually making testable predictions. That's real science right there.
This is all incredibly fascinating, but one thing I'm still struggling with is this idea of complicate particles. If protons and neutrons are made of even smaller particles, why can't we see those particles directly? Why are quarks always trapped inside those bigger structures?
That's a great question, and the papers actually address this using the idea of destructive wave interference.
Destructive wave interference. Now, how does that work again?
Remember how waves can either boost each other up with constructive interference or cancel each other out with destructive interference? It's like those noise-canceling headphones using opposite sound waves to block out noise.
Oh, right. So it's all about waves being in sync or out of sync.
Exactly. They suggest that in those composite particles, like protons and neutrons, the wave centers are arranged in a way that creates a ton of destructive interference. And that interference, it basically hides those individual particles, makes them undetectable. They're kind of like camouflaged.
So it's like a group of singers perfectly harmonizing. You can't hear each individual voice. You only hear the blended sound.
Perfect analogy. And that's why we haven't been able to isolate quarks, they say. It's not that they're tiny balls bouncing around inside, but rather something that emerges from the way the whole composite particle breaks down.
Okay, so quarks aren't actually particles in this model, but more like a consequence of how those composite particles break apart. That's a pretty big shift in how we think about things.
It is, and it actually helps explain some of those weird things about quarks, like how they have fractional electric charges. You never see that with particles that exist on their own. But if quarks are just an emergent thing, those fractional charges could just be a reflection of the overall charge of the whole structure.
Like cutting a cake into uneven slices. Each slice has a fraction of the total cake, but the cake wasn't made with fractions to begin with.
Exactly. This model makes us rethink what a fundamental particle even is. Maybe some particles are just emergent properties, not fundamental building blocks.
This is really making me question everything I thought I knew about particle physics. But if this model is true, what are the biggest implications for how we understand the universe?
Well, it's early days, but if this holds up, it would be a huge change in how we see the universe. It might mean that our current understanding is, well, incomplete, and that there's this deeper, more fundamental level of reality based on this vibrating space-time lattice.
And if that's true, wouldn't that mean everything in the universe is connected through this lattice?
Exactly. If everything comes from these wave centers, and all the forces come from how those waves interact, then everything is linked. It's like we're all part of this giant cosmic web connected by these threads of energy.
Wow, that's a pretty profound thought. But I have to admit, all this talk about wave centers and space-time lattices can be a bit abstract. Is there a way to think about this model in a more concrete way?
Oh, definitely. Remember how we talked about those equations, the ones based on sound waves and vibrating strings? They think that connection to classical physics might not be a coincidence. They suggest that there might be this deep similarity between how waves work on the big scale and how they work at the quantum level.
So it's like the universe is playing the same song, whether it's sound waves in the air or these weird waves in space-time.
That's the idea. There's this hidden harmony in the universe, and this model is giving us a peek into it.
Like we've been listening to the universe's symphony, but only hearing certain instruments. And now this model is letting us hear the full orchestra.
I like that. And just like an orchestra can make all kinds of sounds and emotions by mixing different instruments and melodies, maybe the universe creates all the complexity we see by combining these basic waves in countless ways.
Okay, you're really getting my imagination going. But let's circle back to those papers for a second. You mentioned they have actual equations to calculate the energies of particles. How does that work exactly?
Well, traditional quantum mechanics, it uses these things called wave functions to describe particles. They're like math expressions that show how particles probably behave. This new model, it takes a different approach. Instead of abstract wave functions, it tries to calculate particle energies directly from the number of wave centers they have.
So it's more grounded, something we can visualize a bit easier.
Exactly. And the equation they use, it's surprisingly similar to the equation for the energy of a vibrating string or a spring mass system. It's all based on the idea that a particle's energy depends on how fast it vibrates and how many wave centers it's got.
So instead of these mysterious wave functions, they're saying, let's think about particles as vibrating systems and use that to calculate their energies.
Right. And the amazing thing is these simpler calculations seem to give the right answers.
So they can plug in numbers and get values that match what we see in experiments.
That's what they claim. For example, they can get the electron energy right using just those fundamental constants we talked about and the number of wave centers in an electron.
That's incredible. It really makes you think this model might have something to it.
It does. Of course, we need more research to be sure, but it's a very exciting development. It's like a whole new way of looking at the universe, one that could be simpler and more profound than we ever thought.
This has been a wild ride so far, and I feel like we've only just scratched the surface of these papers. But we're running out of time for this part of our deep dive.
I know. Time flies when you're talking about the universe.
It really does. But don't worry, listeners. We'll be back soon to wrap up our exploration of these mind-blowing ideas. And we're back, diving deeper into the subatomic world with these, well, pretty radical research papers.
Yeah, still trying to wrap our heads around all these wild ideas from those tiny vibrating granules
To those particles potentially shaped like pyramids.
And who could forget maybe rethinking quarks altogether?
It's a lot, but one thing that really struck me is how they try to connect the dots between quantum mechanics, which is so weird,
Oh yeah, super weird.
and the familiar world of classical physics, the stuff we see every day.
Yeah, like they're saying maybe the universe is humming the same tune at all levels, big or small.
Right, like planets and stars following those same basic rules as those tiny electrons.
And a key example is how they use those good old classical physics equations, the ones we all learned in high school.
To actually predict the energies of those subatomic particles, it's amazing.
It is. They basically said, what if we take these simple equations and see if they work in the quantum world too? And, well, it kind of seems like they do.
And they're not just pulling these equations out of a hat, right? They're rooted in this whole space-time lattice model.
Exactly. It all comes back to that idea that particles are like tiny vibrating systems within this lattice.
So their energy depends on how many wave centers they have and how fast they're vibrating.
You got it. Instead of using those super complex wave functions that quantum physicists love.
Which are, let's be honest, kind of hard to grasp.
Oh yeah, super abstract. They're saying, hey, what if particles are like tiny strings or little masses and springs, and we use that to figure out their energies?
It's like taking something incredibly complex and finding a simple, elegant way to describe it.
Exactly. And the best part, it seems to work. When they crunch the numbers using these simple equations, they get results that match up with what we see in experiments.
So they're not just theorizing, they're showing that this model has real predictive power.
Exactly. And that's what makes a good scientific theory, right? It has to make predictions that we can test.
Okay, so let's play a little game of what if. What if this model is actually right? What would that mean for our understanding of the universe?
Whoa, that's a big what if. Well, it would mean that our current picture of particles and forces is incomplete.
Like we're missing a big piece of the puzzle.
Yeah, and that there's this deeper level of reality, this vibrating space-time lattice underlying everything.
And if that's the case, everything in the universe would be connected through this lattice, right?
Exactly. Imagine it, everything from the tiniest particles to the largest stars, all interwoven through these vibrating waves.
We'd all be part of this giant cosmic dance, connected by these invisible threads of energy.
This is a beautiful thought, isn't it? But let's not get too lost in the philosophy here. What about the practical side of things? Could this model lead to new technologies, new ways of understanding the world?
Yeah, that's what I'm really curious about. What could we do if this model turns out to be true?
Well, if we can crack the code of this space-time lattice, understand how these waves work at the most fundamental level.
Like really unlock the secrets of the universe?
Exactly. Then we might be able to manipulate energy and matter in ways we can't even dream of right now. It's like discovering a whole new set of rules for the game.
So new energy sources, new materials, maybe even devices that operate on principles we haven't even discovered yet?
Exactly. It's early days, but the possibilities are mind-boggling. It could spark a whole new technological revolution.
It sounds like we're standing on the edge of a whole new era of scientific exploration.
And these papers, they might just be the catalyst that pushes us over that edge.
I want to give a huge shout out to our listener who sent in these papers for this deep dive.
You've taken us on an incredible journey.
A real mind-bending adventure into the heart of the universe. And to everyone listening out there, keep exploring, keep questioning, and keep those amazing questions coming.
Because who knows what other mysteries are waiting to be unraveled out there in the vast cosmos. A CCA